So, Turing machine, very simple model, right? Very simple to simulate. So you can write a C program to take a state table and a set of input and treat it like a Turing machine and basically execute this program and see what the input gets changed into. And it's not a bad program to write. If you want to play with strings sometime, it's a good exercise. And there's a bunch of these available on the web. So this is the one I usually pick on. Turing machine simulator. And you've got your tape up here, the head moves back and forth, and here's the program. They modified the Turing machine so you can put comments in, yay. Because without comments, this would be really, really, really hard to read. Now it's just really, really hard to read. And they make some embellishments. They allow wildcards and things like that, but it's the same basic setup. So if we run the state machine, we get a little smiley face out. So that's kind of cool. And it took 38 steps. Well, they have sample code. So let's do binary addition. And so here's our input. Well, let's make our own. So what numbers do we want to add?
27 and 9.
27 and 9. Okay, so what's 27 in binary?
16 plus 8 plus
3?
Yeah.
Okay. And then 9. I don't know if they have to be the same number of bits, but I'll write them both as 5-bit numbers. So we're doing 27 and 9. So what does that turn out to be? Here's the pop quiz. 36. Okay, so that should be 32. Should look like that. 100, 100. All right, so let's go ahead and load in our tape, and let's run this. Did I mess up? Yeah, 24, 27, and 9. Okay. All right, so I mean, it's showing you what steps it's executing, and that was pretty quick. So there's our answer, 36. Took 99 steps.
What were the X's and Y's?
Temporary markers, so you can write any symbols you want, and it's using those to basically save its progress at some point. Right, so if you wanted to take something and copy it somewhere else, you might put a X at that location and then move over to some point where you want to write it and put a Y there, and now you have those spots marked and you can go back to where you were by just looking for an X or looking for a Y. So let's do binary multiplication. So let's do, how about 5 times 7? 7 times 5. And let's run that. Now this has got to be able to do addition, right? But it's also got to be able to keep track of where it is. It's got to be able to do some shifts to move things over and make some temporaries. And so this is going to take more than 99 steps. That's just 7 times 5. But it's going to run for a little while. There we go. 481 steps. And that looks like 32 plus 3 is 35.
Run it at full speed. Do it again.
So that's not bad.
And then you throw that into the, like, 2 point some gigahertz.
Yeah. So let's do the primality tester. So let's see if 5 is a prime number. Because we can multiply, we can divide, and then we can loop, and we can test over. So this is a little bit of a long program, including comments. It's 224 states. Well, 224 statements, 616 states, but they're not all sequential. So let's run that. This is testing the number 5 to see if it's prime. And let's go ahead and run this at full speed. There we go. So 1,500 states, and it tells us it's prime. So give me a bigger prime.
11. 39.
Let's do, what one?
Nothing.
37.
Or 37.
Let's do 37, okay, so 32. It should be 37. So we'll run this at full speed. It's an infinite tape, so you never run out of memory, which is a nice feature. And I have no idea what it's doing. But you know, it's got to keep track of some temporary variables, and it's probably using some of these alphabetic symbols to delineate one temporary variable from another. But I mean, your basic operations are really simple. Find the symbol, look at your state, write a new symbol, move the tape, go to a new state. But that's enough. So it's a little shorter to write it in C, and it probably runs a little quicker. This will finish sometime during the lecture. I don't think it's more than a few minutes actually, but we can just let that run. Because it's such a simple way to do computation, it's easier to do things like try to prove theorems about what you can or cannot do with a Turing machine, as opposed to a C compiler, which is a more complex syntax and more symbols and so on and so forth. So when you want to study computation, Turing machines are a nice thing to use. When you want to actually write a program, they're not really your first go-to, right? By the end of 223, you'll probably never want to use C again. Maybe you already don't, I don't know. But you know, once we spend some time in Java, it's like, it's a totally different experience. It's as different from C almost as C is from this. I can't tell if it's getting close or not. Somewhere in there we could see like what divisor it's up to, and it's got to get up to probably 5 is the largest divisor. Good comment. This is very inefficient and slow, so be prepared to wait. All right. So one thing that that Alan Turing was studying was one of these Hilbert's problems from the end of the 1800s. David Hilbert posed a series of mathematical problems that he suggested we should work on for the next 100 years to move mathematics forward. And one of these problems was basically, it's what we now call the halting problem. It's done, yay, it's prime, cool. 74,351 steps. So that's not bad. That might be on par with how many clock cycles it takes in the CPU, I don't know. Because you know, CPUs do really simple things too. They do and or and not and XOR. But they do a lot of them really fast.
Throw another one in, just let it run.
We'll just let one run in the background. So that's to the 11th minus 1, I believe, which is the first non-prime Mersenne number. Cool. So the halting problem is a really simple statement. Okay, here's the basic question. Can you write a program that will look at another program and tell you whether or not that program ever exits? So, you know, you turn in your program to a teacher, and the teacher can look at it, and sometimes they can say, oh, you've got an infinite loop in here. Right? You said, well, x is bigger than 0 instead of, well, x is less than 0. And so sometimes you can look at a program and you can say, oh yeah, okay, this will run, it'll take a while, and then it'll eventually exit, or you can say this is going to loop forever, right? So the question is, can you write a program that does the same thing? You show it the source code to a C program, you tell it what you're going to type in if it's got any inputs, and it tells you in a finite but possibly really long amount of time that either eventually this program will exit or it's going to loop forever. That's the goal of the halting problem. Can you write a program that'll do that? Or can you come up with an algorithm to analyze, say, a C program, tell whether or not it halts? The original formulation was on Turing machines, right? So we know that Turing machines halt when you go to a state that's not defined. So by looking at the state table and the original input, can you tell will the machine eventually halt or not? And
State is only in the 60s. It's rarely going out of it.
yeah,
60, 62.
that'd be a fun exam question to like reverse engineer this program. Be like your bonus question.
200 lines.
That'd be a cool group project actually. Like if we had like a longer term, we'd have like a big group project to like take one of these things apart. So so can you write a program that tells if a C program will halt or not? And Alan Turing proved that you could not do this. It's impossible to write such a program. And let me give you a sketch of the basic proof, and not everybody believes this proof is valid. But here's the basic idea. So here's my magic halting program. And it takes, you know, a program as input, and it takes the things you're going to type in when the program's running, and it does some stuff. It does some analysis. It consults a genie and all this kind of stuff. And eventually, in some finite amount of time, it's going to give you an answer. And it's somewhere in its code, it's going to say it halts. And somewhere else in the code, there's some set of logic that concludes with it printing out the statement, it runs forever. And there's other stuff in here, and there's the end of your program. And we can assume it's just one big main program, no modularization anywhere, right? So just a big program. Okay, so here's what the proof that this program does not exist does. It says, okay, suppose you give me this program, and it will solve the halting problem on any piece of C code. Okay, I'm going to modify this. I'm going to add something down here. After it says it halts, I'm going to say while 1 equals 1, and I'm just going to have an infinite loop.
Does the program you give it have to be finite, I'm guessing?
Yes, it's got to have a finite length. And down here where it says it runs forever, I'm going to put an exit statement after it prints that out. And now I'm going to ask this program to analyze this. Right? And one of two things are possible. It has to reach a conclusion in some finite amount of time. So 5 billion years from now, it reaches its answer. And suppose it decides this program is going to halt. It's going to print out, yep, the program halts, and then it's going to enter an infinite loop. So if that's the conclusion it came to, it was wrong, because in fact the program will never halt. But if it concluded that the program is going to run forever, the next thing the program does is it exits, and again it got the wrong conclusion. And this is a return to this diagonalization argument that we looked at really briefly at showing that there's more real numbers than there are integers. You sort of set things up in a way, and then you put a little twist in that basically takes the claim that this thing works and forces it to break whatever it is that you're trying to make work.
But then, if you do put in this program into this program, couldn't you make it so that you're putting in the inputs or whatever,
Mm-hmm.
and then it will check the program for statements like that and different sort of things. And if it sees that, then it will exit. Or, in this case, it will see that there is a statement like that, and then it would go down to it goes on forever, and then it would end.
So I'm going to put this thing after every place that it prints out, it's going to halt. And I'm going to add an exit after every place that it prints out, it runs forever. So even if I have some other section or code over here that says, oh, this is that tricky program, right? If it concludes it runs forever, I'm going to throw an exit statement after that.
But then wouldn't you have to input what the code would take as parameters so it could, it could predict whether or not it would halt, and then it would go on forever, and then it would print out it goes on forever, and then the program would end.
But I'm going to take that modified program and feed it that modified program. And this is a proof you find in a lot of computer science textbooks, and you may be brushing against the thing that bothers me about this, which is if you claim that magic HP solves a halting problem, you're not necessarily saying that when you add these statements, it still solves the halting problem, right? Now, traditional C programs, if you add something after a print statement, it doesn't change what the print statement does. It doesn't change all the logic up here, right? But funky programs that do other things very likely could do something different just by adding something down here. In the same way that sometimes adding a print statement makes your bug go away. You run your program and it seg faults, and you put in a print statement and it's not seg faulting anymore, right? Yeah.
The thing that's confusing me is that wouldn't it only break if what it was trying to determine what it included itself?
Yes. And that's exactly how you break it, is you ask it to analyze itself.
But then couldn't you reliably prove, I think what he's getting at is, couldn't you reliably prove that this works for everything but itself?
Possibly. But the full halting problem has to work for every single program.
But what if you feed the modified one into the non-modified one?
Yeah, this doesn't show that that would fail. And to me, if I had a halting problem solver that worked on almost all programs, I'd be pretty happy.
Wait, isn't this like that proof we did in class that ended up being like the paradox?
Yeah.
Where it's like,
If it's self-consuming, then it
Yeah.
can't contain itself. Yeah. It's the same kind of diagonalization thing. And this is weird, and I've never bought into this. It's bothered me, and about 3 years ago when I was teaching this in 215, I tried to explain why it bothered me, and I went off and I actually wrote a paper on it, and so that paper is online. But I tried to submit it to a journal and got back reviews saying things like this person has no understanding of mathematics and stuff like that. So I don't have the language to formalize my objections to this, but more precisely, I don't have the background to really understand the formal proof of the halting problem. I'm pretty sure if I did, then my objections would be answered, but I think I'd have to take a course in some kind of logic course. Or get somebody to figure it out for me. But the general consensus is you cannot solve the halting problem, and it kind of makes sense, right? Because if you had such an oracle that could tell you if a program halts or not, you could answer all kinds of unknown questions. For example, is there always twin primes, right? 5 and 7, 11 and 13. Can you always find 2 primes that are separated by 2 no matter how large you look? Is there some number, 17 gazillion and 6, after which there's no more twin primes, right? Well, you could write a program that, let's see, let's just do Goldbach. Goldbach's conjecture, forget about twin primes. So you wrote a program that tries to write even numbers as a sum of 2 primes. Okay, so did you put anything in your program if it can't write an even number as a sum of 2 primes? Did you have it print something or do anything special? Send you a text message?
Yes.
So you could write your program, and instead of just taking in a number and testing that many even numbers, have it test numbers forever. Unless it finds an even number that can't be written as a sum of 2 primes, and in that case, just do a return, just exit. Well, print out the number and then exit, right? So now you have a program, if it ever halts, you know that there's something that violates Goldbach's conjecture.
I'm going to disagree with that
Yeah,
because of the book that you gave me yesterday.
yeah.
Are we assuming computer science is a subset of pure mathematics, or that it's its own thing?
I don't know.
Because if we're assuming computer science is a subset of pure mathematics doesn't actually have to give you any meaningful result. It just takes a set of assumptions and prints out what you can do with those.
This is true.
So if we're looking at this really abstract mathematics, we're taking in all sorts of, we're looking at the program, the halting program, as something that looks at propositional logic and provides proofs.
Mm-hmm.
At pure mathematical level, what it's doing is it's taking assumptions and telling you what you can do with those. And in pure mathematics, you can do that and not have to worry about whether or not those are even true. That's the whole beginning of Gödel's theories.
Right.
We're assuming that these things have to be true, but what if in mathematics we don't actually care about the truthiness of whatever pops out? And if that's the case, you can write a halting program that will look at Goldbach's conjecture, tell you if it halts or not, and the program could run perfectly and spit out gibberish. The program still does what it's supposed to do. It's just you're trying to pull meaning out of it that you shouldn't be trying to pull meaning out.
But if you write the program correctly, why can't you pull that meaning out?
Because you don't care about what the output is. It's pure
You do
mathematics.
care.
You're taking in the axioms. You're putting out outputs, and you don't care about the truth of the output.
Interesting. All right, let's talk about it offline. Yeah, let's talk about that. But if you think of this as just computer science, right? You can write Goldbach's conjecture, and if it finds an even number that can't be written as a sum of two primes, your program will halt. Otherwise, it'll run forever. Feed it to your genie, and if it says the program halts, you know there's something that can't be written as a sum of two primes. If it says it runs forever, you know everything even number can be written as a sum of two primes. Yeah.
Seems like it would need to know whether Goldbach's conjecture is true or not to know whether it's false.
Well, depends how you write this halting program, right? So this thing that analyzes a program and tells you if it halts, presumably you don't have to tell it what the purpose of the program is. It's just looking at lines of C code, for example, or assembly code or something, and telling you, you know, I've detected an infinite loop here. But effectively, right, it's solving Goldbach's conjecture in some way.
But then it tells you it halts and you realize it's because of an overflow.
Yes, so that's another problem, is a C program can only go up to a certain amount, right? It's only got a certain amount of memory. And if you've got 16 gigabytes of memory, that's 16 billion bytes. That's 128 billion bits. That's the largest integer you could hope to store.
But a computer's a logic state machine, right?
Yeah.
And we've already proven earlier in 215 using Gödel's theory that you cannot apply logic rigor to mathematics. That's like the
Yeah,
whole
you
point.
can.
Well, but not to that level.
There'll be incompleteness or there'll be contradictions,
Right.
but I think those are like out there.
But if we're looking at like a system that only works with finite propositional logic, it's finite logic, it's not
Right.
undecidable logic, then there's a big chunk of mathematics you can't even throw into it. And it's not a failure of the program, it's a failure of the fact that those problems are undecidable already, so trying to throw them into a finite machine that works on finite logic with
True.
something that's outside the
Mathematics you're
barrier.
using aren't necessarily the ones that can't define with logic.
Right.
There is mathematics that you can define with logic.
Right.
Like
And
you
this-
can logically prove that 1 + 1 = 2, for instance.
Maybe.
I think we have proof for that.
Yeah.
You
But
can't prove all of it.
all those proofs start with axioms anyway.
You can't really start anything without one, though.
Yeah, presumably, although I don't know if I believe that. That's pretty philosophical, though.
How would you be able to start without one?
Well, I don't know, let there be light. I don't know. I don't know how that can happen, but I wonder if it can.
Because a proof always has to take an input, and if you start without an axiom, then you don't really have a way to manipulate any input.
Well, so I think that's a good question. Is there such a thing as something that doesn't come from an axiom? Is there
Because if you
any
can-
axiom that's actually not an axiom that we actually know is true, and we don't have to simply assume?
Are you talking about like a proof that has nothing given?
More like you know, when we do induction, we say algebra. You know, we're properties of integers because we're assuming those things are true. But if you boil it down, do you always have to assume something, or could you actually like have a system of mathematics without any assumptions? Is there something that's fundamentally true whether we assume it or not?
And then from that, you can draw the axioms.
Yeah. And I don't know if that's true or not. I'm guarantee a lot of people have studied that, but I just don't know. It's just kind of ponderings. So let's finish up with Turing machines because we've got like 10 minutes left. And I will not put Turing machines on your exam. We'll talk about your exam on Friday, but this is just for fun at this stage. So speaking of oracles and genies, so a Turing machine is the Turing machine we've been talking about is something that's usually called a deterministic Turing machine. The behavior of it is completely deterministic. There's no randomness inside. You can look at the state table and the inputs, you know exactly how it's going to perform, how it's going to move from state to state. Okay, so that's a deterministic Turing machine, or DTM. Okay, there's another thing called a non-deterministic Turing machine. And this is a Turing machine that has a genie inside. And the genie can help you figure out what your next state should be. It's a friendly genie, so it makes these recommendations in order to speed up your computation. So for example, you have a state table, but you're in this state and here's a symbol under. Your next state could be, I don't know, state 4 or state 7 or state 518. And I don't know which state I want to go to, because 2 of those states will take me a really long time to reach an answer, and will eventually get to the other state, which is the one where I actually discover my answer. The genie will help me make that decision, and it will say, oh, you should go to state 17. And I go there, and bingo, my problem is suddenly solved. Okay, so it's a Turing machine with magic inside. We don't have these things. But here's why we study non-deterministic Turing machines. There are classes of problems called decision problems, yes-no problems. Okay, problems that simply look for the answer to some question where the answer is either yes or no, as opposed to what is the shortest path from here to there through this graph. I'll go to A and go to B, right? A yes-no question would be, is there a path shorter than length 25 from here to there? And the machine would say yes or no. Okay, if you had such a genie, and you could ask it yes-no questions like that, you could find the shortest path from one point to another really quickly. The length of the shortest path. You'd add up the length of all your edges and you get, 519. So you say, is there a path shorter than 519? And it says yes. Is there a path shorter than 518? Yes. 517? Yes. You keep going till it says no, and now you know the length of the shortest path. It was 207, because at 206 it said no. And what's the order of complexity of that? That's order n, where n is, say, the total distance if you travel along all the edges. So when you study the theory of computation, we talk about classes of problems, and there's a class called P. And a class P problem means you can solve this problem in polynomial time. So what's a polynomial? It's n raised to some integer times some constant, plus n to another integer times some constant, and so on and so forth. And we know constants don't matter, and we know smaller terms don't matter. So polynomial time is basically order n to the k, where n is the size of the problem that you're solving. Now k might be big, it might be n squared, it might be n cubed, it might be n to the billionth, but all of those are considered polynomial time. This is good. Okay. Things like this, or this, or this, those are not good. Those take you a really long time. So we like problems, we like algorithms that are polynomial time. So a class P problem means it's solvable in polynomial time on a Turing machine, which means a laptop. There's a class NP, which means polynomial time on a non-deterministic Turing machine. Means if you have a genie, you can solve this problem in polynomial time.
If you had a genie, couldn't you solve it in one?
Not necessarily. This genie only helps you, it helps you go to an efficient state in your Turing machine. But there's some problems that it's pretty hard to take advantage of that. But a lot of problems will fall to this. So like traveling salesperson, what's the shortest path from here to here that goes through all the cities? And you can just keep asking, is there a path shorter than this or that? And in polynomial time. So two separate classes of problems? Well, there's a famous theorem which asserts that there's a subset of NP which is called NP complete. And if you can solve any problem here in polynomial time on a regular Turing machine, you can solve all of these problems in polynomial time on a regular Turing machine. In other words, all the NP complete problems are equivalent to each other in some way. It's still working. Sorry, computer.
It's kind of going.
It's kind of getting there.
It's getting closer, yeah.
So here's some of the NP complete problems. So lots of mathematical problems. Those aren't too interesting. Hamilton completion, Hamilton path problem, partitioning problems, bin packing problems, Battleship, Bejeweled, Bulls and Cows, Candy Crush, Donkey Kong. So these are the good things, right? So all of these are NP difficulty, but if you can find a polynomial solution for any one of them, you can find a polynomial solution for all of them. And so this is a standing problem. Is NP the same as P? And it's an open question. And it's one of these questions that people who aren't, trained experts in this field still go crazy coming up with like ways that they might try to prove it. It's a really fun recreational exercise. And the consequences of showing that P and NP are equivalent is mind-boggling, right? Assembling an optimal Bitcoin block, for example. It's one of those totally world-changing kind of things.
But what, so if P and NP are equivalent, what does that mean?
It means that we can take these problems that are really, really time expensive to solve, and we could solve them in polynomial time. And it's got implications for crypto systems and electronic currencies and all kinds of
If the
stuff.
polynomial time is massive, then...
But still, it's a huge... It means, in some sense, there's a path, right? N to the billionth is really massive, but it's still fundamentally different from n factorial. Because if n gets big enough, that n to the billionth is minuscule compared to n factorial. So it almost puts a bounds on how large these problems can grow and still be considered hard. And a lot of our society and culture depends on the hardness of solving some of these things. So this PNP problem is one of those big questions.
And so if it was solved, what would the next step be?
You get a knock on your door from Men in Black and they have a conversation with you. I don't know what the next step would be. There's lots of fiction written about this, about what happens afterwards. But I think it would be applying that polynomial time solution to some of these and coming up with those algorithms.
And saying if it's even worth it.
Yeah, but I think you'd learn something about algorithm construction in the process.
Do you happen to know what pancake sorting distance problem for strings is?
I don't happen to know, but there's a reference to it. Prefix reversals on binary and ternary strings. I used to know this. All right, I'll see you Friday.